Hello, hello, can you hear me? Hello, am I audible?
Yes, sir. Yes, you are.
Okay. Yeah, so we have like few students, so we'll wait for 2 more minutes. After that, we'll start the session. Okay.
Okay, sir.
Okay. So yes, we will begin the session. I think we have sufficient number of students here. Okay. So in this session, we'll be discussing week 5 concepts. Okay. So before we begin, how many of you have watched the entire lectures of week 5? Please raise your hand if you watched the entire lecture of week 5.
No, sir.
Haven't watched. Okay.
I have not watched, sir.
Okay.
Just 3 videos, 2 more videos.
Okay, only one of you have watched. How many of you watched? One, some say yes, others?
Halfway through, sir.
Halfway through, okay. Here Raja has watched. Okay, so how many of you watched at least 3 lectures? At least 3 lectures. 3 or more, you can raise your hand. 3 or more. Okay, even this was less. Okay, all right. So anyway, we'll start with the session. Okay, so we'll discuss the concepts. So for those of you who haven't watched, you might not be able to follow entirely, but then Please try to be attentive. Okay, once you have watched the once you've gone through this live session, it might be easy for you to understand the lectures and follow through it easily. Okay. So let me begin the session. Okay. Share my screen. I understand that week five slides were not shared with you, right? Week five lecture slides were not shared with you. Am I correct?
Yes, sir.
Okay. Okay. We look at the slides and then we'll discuss those concepts which were discussed in the lectures in detail. All right. Are you able to see the screen?
Yes, sir, the screen is visible.
Yes, sir.
Okay. Okay. So for those of you who have watched the week 4, I mean, who has gone through until week 4, week 5 is almost similar to week 4. Okay, whatever you've gone through, the diagonalization, the orthogonal matrices, okay, and then symmetric matrices, all those things are going to come here, but then with the different names. There you have seen the matrices and understood them with respect to the real numbers. Here we just deal with the complex numbers. Okay, that's the only difference across these two. Okay, remaining everything almost appears to be the same. It's kind of like so suppose let's say in the real in the with the real numbers, right? You have the symmetric matrices here with the complex numbers. You have this Hermitian matrices. Okay, you could consider this real numbers as I would say special case of complex numbers. Okay, and then for the like just like brief introduction. Okay, if you do not understand these terms, it's okay, we'll get into that. Okay, for symmetric matrices we have parallelly Hermitian matrices, and for the orthogonal matrices, right, you have this unitary matrices. Okay, like you'll be able to do the diagonalization of the symmetric matrices using the orthogonal matrices. You'll be able to do the same thing here. Okay, so our entire week 5, right, it will be there until the diagonalization of this Hermitian matrices. Hermitian matrices is nothing but the complex number case of this symmetric matrices. Okay, at least the brief idea is clear. What is there in week 5? Is that clear?
Yes, sir.
Okay, so yeah, whatever you have seen in week 4, it's going to be the same. I mean, it's going to be almost similar case of it, but then looking at with respect to the complex numbers. Okay, that's the only difference. Okay, so let us begin. So the first thing is the difference between this complex number and this real number is this: we have this imaginary part. Okay, we have this imaginary value called I. Okay, so imaginary value is the square root of -1. Okay, the reason why we even study this complex matrices is that this complex matrices, I mean, these complex numbers will be helpful for us to solve some particular problems in the physics science. You know, in general, easier to solve and understand. Okay, it makes so many complicated problems easier to solve. Okay, that's the only purpose of this using these complex numbers. These complex numbers, it has been like applied to various fields. Okay, so the way you represent this complex number is of this, which says c equals to a plus ib. Okay, so here I equals to square root of -1. A and b you could consider them as real. Okay, a and b are real numbers. Okay, so since you have this I equals to square root of -1, okay, and since you know that square root of -1 is not defined in the real world, that is the reason we call this I as imaginary. Okay, imaginary. So and c equals to a plus ib is called as this complex number. Okay, so the real numbers are also a complex number. You could assume with p equals 0. Okay, if you take this b part as 0, so then c will be equals to a, right? A is a real number. So basically this real numbers are what you say, real numbers are subset of this complex numbers. You could consider it that way. Okay, is it clear what I meant by real numbers are subset of complex numbers? Because for the real numbers, you won't have this imaginary part. Okay, this imaginary part will not be there. That's a real numbers. If you have the imaginary part, then that is called as complex number. Okay, until now is it clear?
Yes, sir.
Yes, sir.
Okay, so exactly why we are using this I equals square root of minus 1 and then why exactly square root of minus 1? That part the scope of it, it's like is like beyond the scope, but then even the only thing that matters for us is that assuming this I equals square root of minus 1, and like proceeding further, it will help us to solve so many problems. Okay, so many real world problems. Okay, easily. Okay, so we have this c equals to a plus ib, right? So this is complex number. Okay, so
Sir,
the way we
sir.
present the yes.
So basic question. So complex, this I equal to root of minus 1. For example, if I say I equal to root of square root of minus 25, minus 27, or minus 33, all these are come under complex numbers, but I equal to root of minus 1 is the only scope for this course. That is what you are saying, right?
See, the thing is, even if you have this I equals to square root of what minus 25 or whichever one you're saying, right?
Minus 27.
It can be written as minus 1 into 25, right? Which is nothing but 5 into square root of minus 1, right?
Oh, okay.
Okay. So basically, the square root of minus 1 is this imaginary part. Okay. This is the only thing that doesn't exist like in real. Okay. You could like this square root of minus 25 is like what? Some numerical multiplication of the square root of minus 1, right?
Yep.
Okay.
Understand. Yep.
So using the square root of minus 1, it actually leads us to like n number of possibilities. Okay. Until now we are restricted by the square root of minus 1. Okay. Once you assume that square root of minus 1 is imaginary and then like proceed further, you'll be having like you'll be exploring into this whole new different world, I would say. Okay.
Yeah. Understand. Thanks.
Yeah. Okay. Okay, so we have this until now we got this. We established that real numbers are a special case of complex numbers where we have this b value as 0. Okay.
Yes, sir.
So yeah, so the way you represent a complex number is, say we are talking about one single complex number. Okay. You could consider this as kind of like we can represent this real value. You'll be representing real value in this x-axis. Okay, this x-axis is called the real axis because we represent this real number in this way, and then this y-axis we use for imaginary. Okay. These four represent this imaginary axis. Okay, so for this a plus ib, the way you represent is here we have this a, and then here you have this b. So this dot, right? This is the complex number a plus ib. Okay, this is the origin. This is this 0 plus 0i. Okay, or it's nothing but 0. Okay. So this is the complex number. I mean, this is the way you represent the complex number in a 2D plane. Okay, this is just a single. This is not a point. This is just a single complex number. Okay. Remember that this is not a point. Okay, this is kind of like similar to a point because you could assume this as point of less a comma b. You could assume it like this. Okay, but then a comma b is a point. A comma b is a point that used to represent this complex number a plus ib. Okay, clear until now?
Yes, sir.
Yes, sir.
Okay. So the modulus or the length of a complex number. What do you mean by the length of a complex number? That is the distance from the origin to that particular complex number, right? So what is the distance from it? So this is a and this is b. This gives the distance as a square plus b square, right? Okay. R square, where r is the distance. So r square will be equals to a square plus b square. So b square. Okay, this. Okay, and this theta is this theta is the angle of this complex number. Okay, and there is this another way of this representing complex number. You can represent complex number as a plus ib, or you can represent it as r e power I theta. Okay, this is nothing but e power I theta is sin theta plus I cos theta. Okay, clear?
So,
Okay, the sin theta is nothing but no, it's cos theta plus I sin theta. Sorry, it's cos theta plus I sin theta. Okay. Okay, so cos theta is nothing but a by square root of a square plus b square. This r is nothing but square root of a square plus b square, right? Okay, and this cos theta is nothing but a by square root of a square plus b square, and then similarly sin theta is b by square root of b square plus b by square root of a square plus b square, and then by dividing it, I mean by substituting the value of r and then cos theta, you will get the same value of a plus ib. Okay, the square root of a square plus b square gets cancelled out, and then you get the same value of a plus ib. Okay, this is just a different way of like representing this. I mean, this is just like using the length that is the distance from the origin, and then the angle using this. All we need is only this, right? We just need the distance and then the angle with respect to the x-axis. Using that, you can represent any complex number. Okay, clear until now?
Yes, sir. It
Okay.
is like the polar representation thing. that
Yeah.
we use.
Yes, exactly. It is like the polar representation. Okay. Okay. So now we have this something which is defined as this complex conjugate. Okay, the conjugate of a complex number. You have established that for a complex number a plus ib, right? I mean, this is the complex number that point represents complex number. So the radius is, the distance is r, and then the angle with which makes it with respect to this real axis or the x-axis is theta, right? Okay, we have something which is defined as conjugate of a complex number. Okay, the conjugate of a complex number is nothing but, let's say we have this complex number as a plus ib. The conjugate of it is defined by as a minus ib. Okay, this is theta. I mean, the same angle theta, but with respect to the different direction, the opposite direction, right? This is like minus theta. Okay, so this complex conjugate, let's say C is a complex number, right? And complex conjugate, it is defined. I mean, it is represented as C bar. Okay, complex conjugate is nothing but r e power minus theta. Okay, or you could write it as r e power of I of minus theta. Okay, which is nothing but a minus ib. Okay, the important property you could notice here is if you multiply c into c bar, right, that is nothing but a plus ib into a minus ib. Okay, this will give you a square minus of ib whole square, right? These are the form of a plus b into a minus b, which gives us a square minus of ib whole square. I square is nothing but minus 1. Since I equals square root of minus 1, I square is minus 1. So which gives us a square plus b square. Okay, which is nothing but r square. Okay, a square plus b square is this distance of this complex number from this origin, right? Okay, so c multiplied by c conjugate, complex number multiplied by its conjugate, gives a square plus b square, which is nothing but r square. Okay, clear?
Yes, sir.
Until now, is it clear? Okay, so we'll move forward. This is a brief introduction of this complex number. Okay, and similarly the complex vector, it is just a just like real vector, like where real vector is the real vector is represented by this Rn, right? Okay, n-dimensional n-dimensional vector which contains these real values.
Sir,
Yes.
sir, complex number and its conjugate, do they form 90-degree angle with each other?
Can you repeat? Complex number and its conjugate.
In the graph, do they form 90-degree angle between each other? The
they?
angle 90-degree angle, do they form that
No,
angle
no,
theta?
they do not actually form 90 degree, right? It's actually 2 theta.
Yeah.
This is theta and this is minus theta. So the total angle between them it's 2 theta. Okay, it's not actually 90 degree. Okay.
Yeah. Okay.
Only when theta equals to 45 it forms 90 degree. Okay.
Okay.
They are not orthogonal. Okay.
Yeah. Yeah.
Okay.
Sir,
Yes.
just to follow up that question, yeah, it might not be 90 degrees, but is it kind of like exactly mirroring of the
Yeah, it is a mirror image, correct.
okay, exactly.
So it is a mirror image with respect to x-axis.
With respect to x-axis, yeah.
Correct. Because this is theta and then this is minus theta, right? It is just exactly the, let's say this is what's this value? This is b, right? This is nothing but minus b. Okay.
Exactly.
So which basically means this is exactly a mirror image of this with respect to x-axis. Okay.
Yeah. Thank you, sir.
Okay. Moving forward, so we have this real vector where we have this, let's say, real numbers, right? Okay, n-dimensional real n-dimensional real vector, right? It is represented as this Rn. So similarly, we have this complex vector. It is denoted as Cn, where each individual vector, right? So we could have this. This is capital and then this is small. Okay, C1, C2, so on, Cn. Okay, so this is nothing but the collection of this n-dimensional complex number, where this could be of this form a1 plus ib1. Okay, this is of this form a2 plus ib2. Okay, here each of this is a complex number. Okay, this is a complex vector. All right, clear?
Yes,
Until now, is it clear?
Yes,
Okay.
sir.
Okay. So we have covered this, and then this linear combination is nothing but this. We have this like we used to do for this complex real vectors, right? We used to do, let's say we have this vectors v1 to vn. Okay, v1 to vn. The linear combination of this vectors is, okay, instead of v1 we could assume it as x1. Okay, let's go with this v1 itself. Okay, a1 v1 plus a2 v2 plus a3 v3, so on, a and bn. Okay, this is the linear combination of the vectors in the real space, right? Okay, these are the real numbers. Okay, a1 to an, they are the real numbers, and these are the real vectors, right? This vi, right, it belongs to Rn. Okay, n-dimensional real vector. Okay, I belongs to 1 to n. Okay, so this is the linear combination of the vectors. Okay, n real vectors. Okay, sorry, I use the same n for this number of vectors on the space, so I will use this as k. Okay, the linear combination of k real vectors. Okay, where each vector of this n dimension. Okay, clear? So this is the linear combination of k real vectors. Similarly, we have the linear combination of the complex vectors too. The only difference is that in place of so okay, I'll just show it to you. Okay, let's say we have this. Let's use the same notation that was mentioned in the lectures, so that it won't be a confusion to you. Okay. Okay, so let's say xi is a real vector. Sorry, complex vector. Okay, complex vector of n dimension. Okay, xi is a real vector. I belongs to 1 to k. Okay, 1 to k. All right. Here to which k. Okay. The linear combination of this k complex vector is denoted as c1x1 plus c2x2 plus c3x3 plus and so on ck xk. Okay. All right. So, but the difference is that here a is a real number, right? Here the c is a complex number. C is a complex number. Here the c1, c2, c3 and so on ck, they are the complex number, and this x1, x2 and so on xk, they are the complex vectors. Okay, clear? That is the linear combination of this complex vectors. It is just the same as the linear combination of the real vectors, but the only difference is that the constant which we used to multiply, right, for getting this linear combination, that constant also, it will be a complex number. Okay, instead of a real number, it will be a complex number here. Clear?
Sir, what does it mean by complex vector?
Complex vector, it is just this, let's say we have this. Okay, I have two complex number, 1 plus I, 1 minus I. Okay, so the complex vector of 2 dimensions, it could be this 1 plus I, 1 minus I. Okay, so this is this two-dimensional complex vector.
Same, just with the I term with it, right?
Yes, exactly. Just like you have for this R2 equals to, let's say 1 2, right? 1 2 or let's say 1 0, right?
Yeah.
The same thing happens with the complex vector, but the thing is, instead of real numbers, you'll be having this complex numbers.
Yeah. Okay. Thank you.
I mean, it could be real also. Some of it could be real also. That is, C2 would be something like 1 plus I 1 also. This is still a complex vector.
Yeah.
Okay.
Okay.
The other way of seeing it is even this can be considered as a complex vector. I mean, ideally speaking.
B term is 0 basically. Then.
Yeah, B term is 0. Ideally speaking, this can be considered as a complex vector. That is why I told you that real vectors or the real numbers are generalization of complex numbers and complex vectors. Okay?
Yeah.
With B value as 0.
Sir?
All right?
Yes, sir.
Sir, this real vectors up to 3-dimensional, we can sort of plot it and see how they show up in the graph, in the plane, in the graph, and the 3-dimensional sphere. But in the complex vector, that how is it seen? Sir? Can it also be visualized in the plane and the 3-dimensional space, like with the that I value is some twisting of that arrow, sir? What is being presented in the 3-dimensional plane for a real vector, that arrow is somewhat angular. That's what contributes to that I value, sir. Is my understanding right?
No. See, the thing is, representation of complex vectors. Complex vectors, it's not easy. Okay, because you could only be representing. See, for
visualization. I mean, visualization of a real vector we see in a 3-dimensional space. Up to 3-dimensional space, we are able to visualize in GeoGebra and other things. But
Correct.
this complex vector, including that I factor, that I is some angular or what? That arrow which we see in the GeoGebra, that is somewhat twisted or what? What is it?
Yeah, that I is nothing but this. You have this. See, I can be considered as this way. Okay, I can be considered as this 90-degree with respect to the real axis. Okay, this imaginary part, it can be considered like 90 degrees with respect to the real axis. Okay, but the problem is here this is one dimension. Okay, these are one dimension, and we have here 2 dimensions, right? And for this to represent this, we again need 2 dimensions. That is this, we again need a real value, and then this complex, and then this imaginary axis will also be there. Okay, so representation of this complex vectors.
Visualization is difficult. GeoGebra.
It's difficult. Yeah.
It is imaginary, so right, everything is like imaginary, right?
Assumption, sir. Is it the assumption? Imaginary means what? We just imagine, like how much is it?
Like, yeah, we just
assumption.
we just take that I equals to square root of -1, and then we proceed to do the
Okay.
do the normal problems like we should do. Okay.
Okay, sir.
Sir, can you please show some linear combination? Means, okay, it's the complex vector is here, but
Okay,
you are
okay.
saying that a complex number means the multiplication
Yeah.
with complex number also.
Okay. I'll show you that. Okay. So before we move on to that, so I'll just show you the addition of complex numbers and then multiplication of two complex numbers. Okay. So let's say I have this A1 plus IB1. This is one complex number C1. Okay. A2 plus IB2. This is complex number C2. Okay. The addition of complex number, it's straightforward. A1 plus A2 plus of B1 plus B2 into I. Okay. This is C1 plus C2. This is the addition of two complex vectors. So even the multiplication of two complex vectors C1, C2, you can consider this. This is just like the algebraic multiplication. Okay. You could just assume that you could substitute I equals square root of -1 and then do the multiplication. Okay. Which will give you A1, A2 plus I square B1, B2. I square is nothing but -1. So I just substitute that here. Minus B1, B2. Okay. Plus A1, B2 plus A2, B1 into I. Okay. So this is the multiplication of two complex numbers. Okay. Clear? This part?
Yes, sir.
This is just a normal. You can just assume this. You can just substitute in the place of I. You can just substitute square root of -1. Okay, and then you can do the multiplication. And once you're done with the multiplication, wherever you have the square root of -1, you can just replace that with I. Okay. Clear?
Sir,
So now,
but still we don't get to minus value, right? Minus, right? A1, A2 minus B1, B2. Why did you get it? It should be A1, A2 plus B1, B2, right?
A1, A2 plus of IB1 into IB2, right?
Correct.
Which is nothing but I square B1, B2. What is it? What is I? I is square root of
-1. Okay,
what
I
is
square, it become I square. Okay.
I square is -1. Okay, that's why you got this minus B1, B2. Okay, and that is the reason why you got for the C dots. I mean, C multiplied by C conjugate, right? A plus IB into A minus IB. It is nothing but A square minus of IB whole square, which is nothing but I square B square. Okay, I square is -1. That is why this became A square plus B square. Okay. Clear?
Yes, sir. Thanks.
Okay. So until now, we have this I square. Okay. We understood the multiplication of the multiplication of two complex numbers, right? Now I'll just show you this linear combination of two complex vectors. Okay. Let's say I have this one vector as 1 plus I, 1 minus I. Okay, and then the other vector as 2 plus I, and then say 1 plus 2i. Okay, these are the two vectors. Okay, now let's say I want to do one complex one linear combination of these two vectors. So this let's say x1, this is x2. Okay, c1 x1 plus c2 x2. I mean, I'm just taking some random numbers. So c1 equals, let's say, 1 minus I. Okay, and then I'll assume the c2 as I can assume this as 2 plus 2 minus I. Okay, I just assume it as 2 minus I. Okay, so what will this be? This will be equals to 1 minus I into 1 plus I, 1 minus I, right? This is c1 x1. Okay, plus of c2 is 2 minus I into 2 plus I into 1 plus 2I. Okay, clear? So you just multiply this 1 minus I with 1 plus I, and 1 minus I with 1 minus I, and then 2 minus I with 2 plus I, 2 minus I with 1 plus 2I. Okay, you get a vector, right? What is 1 minus I with 1 plus I? That is nothing but 2. Okay, yeah, you could just check this out. It will be 1 square minus I square. minus I square is minus 1. So 1 square minus I square will equal to 2. Okay. 1 minus I into 1 minus I is nothing but 1 minus I whole square, right?
Minus 2i.
It will be
2 minus
Minus
2i
2i.
minus 2.
yeah, it's going to be minus 12. Okay. So this 2 minus I into 2 plus I, it's going to be equals to what? 2 square minus I square. So which is nothing but 5. Okay. Plus 5. 2 minus I into 2 plus I is 5. Okay. These are the form of a plus ib into a minus ib, which gives me a square plus b square, right? So 2 square plus 1 square, which is 5. And then 2 minus I into 1 plus 2i, you just need to multiply this. 2 minus 2i square, which gives me 4. 4 minus I plus 2i, 4 plus 3. Okay. Am I correct? This part 2 minus I into 1 plus 2i.
Yes, sir.
Can you check? 2 into 1, 2. Minus I into plus 2i, it gives me minus 2i square.
Yes, sir. Yes.
Okay, minus 2i square is nothing but 2. So it gives me 4 plus minus I into 1 minus I plus 4i. 2 into 2i is 4i. So it gives me 4 plus 3. Okay. So now we just
Sir, 1 minus I
4.
into 1 minus I, it should be 2 minus I, 2i, right? 1 minus I into 1 minus I.
yeah, 1 minus I into 1 minus I. Yeah.
2 minus
It will be
Minus
2 minus 2i, right?
okay. Let me check.
1 minus I whole square, you can make it otherwise.
Yeah. So it will be nothing but 1 square plus I
Plus
square
I square minus 2i.
minus
yes,
2, right?
yes, yes.
1 square I square gets cancelled out.
Minus
I square means square root.
I square is minus 1.
Oh, okay. Yeah. Sorry, it's my bad. I square, I thought it's 1. Yeah, okay. Yeah.
Okay. Yeah, if I square has been 1, then we won't even have.
Right.
Okay. Yeah. But then that is that. So now we just need to add this to complex vectors. Okay. It is just like how you do it for the real vectors. Okay. 2 plus 5 is 7. Minus 2i plus plus of 4 plus 3, it gives me 4 plus 5. Okay. This is the linear combination of vectors. Okay. Complex vectors. Clear until now?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir, clear, sir.
Thank you.
Okay. Sorry for the bad handwriting. Okay, if I'm not able to follow my handwriting, sorry for that. Okay. So one of the important concept we have is we have this concept of length of a vector, right? Correct?
Yes,
The
sir.
length or length of a vector we have, right? That concept we have. Correct? So
Yes, sir.
what do you mean by the length of a vector?
The distance from 0.
Let's say okay, I'm talking about real vector here. I'm not talking about complex vector. So let's say I have this. This is nothing but x1, x2, x3, and so on, xn. Okay. So here x is a real number. Okay. X is a real number. Okay. So what is the length of a? Let me denote this by capital X. Okay. Capital X equals to this one. Okay. So what is the length of this vector? Or let's say square of length of this
x1 square plus x2 square plus x3 square.
Correct. X1 square plus x2 square
Plus
plus
x3
x3
square.
square plus and so on.
X dot X.
Yeah, exactly. X dot X. Or if it is okay, we won't have the square root.
Yeah.
It will be X dot X. Okay. Okay. All right. So what about the case of complex vector? What do you think will be the formula? Okay. Let's do it this way. Huh? So this is nothing but the modulus of this x1, right? X1 square is nothing but the modulus of this. I mean modulus of x1 whole square, right? or the length of x1 whole square plus length of x2 whole square plus length of x3 whole square and so on, length of xn whole square, right? Am I correct?
Yes, sir.
For real vector, similarly we could do this for complex vectors in this way. So let's say we have this length of c1 whole square plus length of c2 whole square plus length of c3 whole square plus and so on, correct? Length of cn whole square. Okay, am I correct? This part.
Yes.
So what is this c1? What is this length of c1 whole square? It's nothing but r1 square, right? R1
Yes,
square.
yes,
Am I correct?
Yes. Yes.
What is R1 square?
A square plus b square.
Yeah. How do you represent that in terms of complex number?
That is
C dot C
a
bar.
plus ib into
C
a
dot
minus.
C dot C bar.
Yes,
C dot C bar equals a square plus b square. That is equal to r square. Correct?
yes, sir.
Okay. So this is nothing but C1 dot C1 bar plus C2 dot okay. It is nothing but how do you represent this? This is x transpose x, right? X transpose x or yeah, x transpose x, right? Yeah, x transpose x, correct?
Yes.
This one?
The dot product, yes.
Yeah. We can't just yeah. X dot x equals to x transpose x. So how do you represent that here? This one?
C1 dot
Okay,
C1 transpose dot C1 bar.
Okay. Could also write it this way. Correct? You could also write it this way.
Yeah. For this.
C1 bar transpose C1, correct? Correct?
Yes.
So this is nothing but the length of the complex vector. Okay. The reason why you always use this conjugate is because let's say you come across the case of 1 plus I mean let's say you just do the normal multiplication c1 into c1 plus that is c1 square plus c2 square plus c3 square. What happens is let's say you have this vector of 1 plus I. Okay, what is 1 plus I into 1 plus I?
1 plus
0, right?
no, 2i, right?
Yeah, it's going to 2i.
Okay.
It is not the length, right? It is not the length.
Yes.
Correct? 2i is not the length of this complex number. Okay? That is the reason why we do not use the same formula of this x1 square. We use the c1 multiplied by c1 conjugate. Okay? Clear?
Yes.
Okay, all right. So I mean the same thing which you have done, that is the inner product or length of a complex vector, right? You could do this inner product with respect to two complex vectors, right? Like you do this x dot y. We could do that for here, right? Correct? So let's say we have this x1 dot x2. Okay, so now we have this. Let's say we have this x. Similarly, y is also complex vector. Okay, y is also complex vector. Now the inner product of these two complex vectors x dot y is nothing but not x1. Okay. X bar transpose y or x transpose, both the same. Okay, both are ideally same. Okay, it doesn't matter. Okay, you do the conjugate and then do the transpose, or do the transpose and then conjugate. It's both the same. All right. This is the dot product of two complex vectors. All right. Clear? Abhitak?
So will we be able to do the other way around as well? Like y bar times x, y bar transpose x. Will that be this?
This one.
Yeah.
See, the thing is, you could do it this way, but then what's going to happen is, let's say we have this x dot y, okay? X dot y we have, and then that is nothing but y dot x, okay? Y dot x is y bar transpose x, okay? The modulus of this, the modulus of y dot x is same as the modulus of y transpose of x, okay?
Yes.
See, if you consider the modulus, both the same, okay? But then directly considering they are not same. I mean, let me give an example. So let me take this x as 1 plus I, 1 minus I, okay? And then y will be 1 plus 2i, and then 1 minus 2i, okay? So let me do this x dot y. What will be x dot y? I need to do the conjugate for this and then transpose, right? So it will be 1 minus I, 1 plus I into 1 plus 2i, 1 minus 2i, okay? Add on the conjugate for this. Conjugate of 1 plus I is 1 minus I. Conjugate of 1 minus I is 1 plus I, okay? And then I add on the transpose for it. So this is going to be equals to 1 minus I into 1 plus 2i. What is that? 1 minus I into 1 plus 2i. It's going to be
1 plus 2i minus I plus 2i square.
3i minus
Plus
1.
I.
okay, 3 plus I,
3i minus 1.
3i, 1 minus 2i square, which is going to be equals to plus 2 minus I plus 2i. So it's going to be 3 plus. So next 1 plus I into 1 minus 2i. What is that going to be? It's again going to be 3 plus, it's again going to be 3, and then
3 minus I.
okay. It's going to be equal to 6. Okay, let's not take this example because it's not going to give us the. I mean, since if it is a real number, then both are going to be same. Okay, but let's take instead of this. Instead of 1 minus 2i, let's take 1 plus 2i also here. So what will be 1 plus I into 1 plus 2i? Can someone tell me?
It is 3 minus I.
It's going to be minus 1 plus 3i, correct?
See, 1 plus I into
1 plus I into
2i.
1 plus 2i. 1 plus I into 1 plus
Okay,
2i.
1 plus 2i. Okay.
Okay, 1 plus 2i, so it's going to be minus 1 plus 3i. So adding these two, what do you get? You get 2 plus 4i.
2 plus 4y, 4i.
4i, correct? So now let's do this. Now that is x dot y, correct? Now let's do this y dot x. Okay, y dot x will be equals to y is 1 plus 2i, 1 plus 2i. So y bar transpose is going to be equals to 1 minus 2i, 1 minus 2i. Okay, so I'm just going to write this here. 1 minus 2i, 1 minus 2i multiplied by 1 plus I into 1 minus I, right?
Yes, sir.
1 plus I into 1 minus I. Okay. You do the multiplication of this. What you'll get is you'll get 2 minus 4i. You can just check this. You'll get 2 minus 4i. Okay.
Sir,
Yes.
conjugate means, yeah. So conjugate means just you made like 1 plus I conjugate 1 minus I, like 1 minus I
Yes.
becomes
Yes,
1 plus I. So
yeah.
and that is kind of like a standard for all the numbers, right? Whatever number it could be. Like for example,
Correct.
let's say minus 3 plus I, then I will make it like a 3 minus I. Exactly.
No. You won't change the. Let's say I have a plus ib. The conjugate of it will be A
A
minus.
minus IB.
Okay, so for the example which you told, minus 3 minus I.
Yeah, minus 3. Yeah, plus IB or minus IB, anything.
Okay. No, you won't have B there. So minus 3 minus I, let's say that is the number. So the conjugate for this is going to be minus 3 plus I. You just change the sign of this imaginary. Okay.
Only that. Right.
Okay, yeah. So for the real numbers, since you won't have this imaginary, right? For real numbers, the conjugate is going to be itself. Okay.
Right. So
Okay,
2 becomes minus 2, minus
Yeah.
2 becomes
Yeah.
plus 2. Okay.
No. 2 won't become minus 2. 2 will become 2 only. Are you getting what I'm saying?
Okay,
So
for real.
Yeah, for real.
But if
for
you
real
want to
number.
make a mirror image of the real number, then for 2, it should be minus 2, right? With
No,
respect to x
see,
axis or with
the
respect.
thing is, when we talked about mirror image, we talked about mirror image with respect to x-axis.
Right.
So the mirror image, let's say this is 2, right?
Okay.
This is 2. The image of it is going to be 2 itself.
Right.
All right.
Correct, sir. Yeah.
Okay. So where are we? Okay, we are here, right? So the let's say C equals C bar. Okay, I mean for a complex number, we have this complex number equals to complex conjugate. What does this say? It means that C is a real number.
Real number.
Yep.
Okay, this is one important part. We'll use this later. We'll use this concept of C equals C bar. We'll use this later part. Okay. So if you do this y dot x, you'll be getting exactly here x dot y, you got 2 plus 4 array. You do y dot x, you'll get 2 minus 4a. Okay. So basically x dot y is nothing but conjugate of y dot x. Okay.
Okay.
Clear? So that is why one student mentioned that can x dot y be already, I mean, can x dot y x bar transpose y can be written the other way, y bar transpose x, right? That
Yes,
cannot
yes.
be. Okay. That cannot be. Right? If it has been real, since if x and y both are real, then x dot y is going to be equal to y dot x. Okay.
Yes.
So that is why the same exact rule doesn't apply here. Okay, the same exact rule which we use for real vectors, that doesn't apply here. Clear?
Yes.
Okay. So now let's just look at some of the properties of the complex vectors. Okay. So this is the first one which you talked about. X dot y equals to y dot x. Okay. I mean y dot x conjugate. All right. Clear? So
Yes, sir.
x dot y is going to be y dot x conjugate. Okay. Generally, what's going to happen is when you do this x dot y, right? Ideally, what do you expect when you do a dot product? You expect a real number, right? But then in case of complex vectors, it could be a complex number also. Like for the example which you are seeing here. Okay. So we got this x dot y, we got it as 2 plus 4, okay. So the dot product of two vectors, I mean two complex vectors, it need not be a real value, okay. But then the dot product of, I mean the x dot x, it's going to be real value. Okay, x dot x, it's going to be real value. All right. Is it clear?
Yes, sir.
Okay. So x dot cy equals c of x dot y. You could just do this using this definition itself. Okay. So x dot y is going to be equals to x bar transpose y. So since this x dot cy is going to be equals to transpose of cy, okay, is going to be c of x bar transpose y, okay, which is going to be c of x dot y. Okay, clear this one? So similarly, if you take this cx dot y, we are going to use this. It's going to be equals to c bar transpose. Okay, I mean, this also you could do, you could check it in the same way. So this, if you follow the definition, it's going to be this one, okay, which is going to be nothing but C bar X bar transpose of Y. Okay, I'm not doing transpose for this C bar because it is just a complex number, right? It's not a vector. Okay, that's why I didn't do the transpose further there. So it is nothing but C bar of X bar transpose Y is X dot Y. Okay. So these are the, I mean, these are three properties. These are like straightforward, but then still we are just emphasizing it. Okay.
Okay.
Clear until now? Any doubts until now? Okay. So the one of the, I mean, this just a notation of it. A star is nothing but the conjugate transpose. Conjugate transpose, either you do the conjugate and then transpose, or you do the transpose first and then conjugate later. Okay, both are same. Both are same. That is represented by this A star. Okay, so A star for a matrix is nothing but conjugate transpose or transpose conjugate of A. Okay, clear? This is just a notation. Okay, this is just a notation. So based on this, you could just write the definition of X dot Y in a different way. So X dot Y is nothing but X bar transpose Y, right? This is nothing but conjugate transpose, right? Conjugate transpose is nothing but X star, right? I mean, the way you represent is nothing but X star now. So X dot Y is X star Y. Okay.
It is just a notification, like
Yeah,
way
yeah.
of like,
This is just a, you could consider it as like a simplistic representation. Okay.
okay.
I mean, you do not want to always write this extra, I mean, X conjugate transpose, all this you do not want to do, right? So it's just simplistic representation. Okay.
Okay.
It just makes it look clean. So you can consider that way. Okay. Yeah. So moving forward, so we have this A star equals to A conjugate transpose, right? The way you represent, what do you mean by the symmetric matrices in the real vector space? What do you mean by symmetric matrices? What is a symmetric matrix? Let's say A. What is the condition for A to be symmetric?
A transpose equal to A.
Correct. A transpose equals to A. So for the complex space, it is nothing but A star equals to A. Okay. A star is nothing but a conjugate transpose or A transpose conjugate. Okay, both are same. Okay. So if this is the case, then it is called as Hermitian matrix. Okay, clear? This is just like in a complex space. If A star equals to A, then that is called as Hermitian matrix. Hermitian matrix is similar to the symmetric matrix way of is
Hello?
I think his
Hello.
voice dropped off.
Yeah. Yes.
Sir, but in Hermitian matrix, compared to the symmetric matrix, there's one conjugate transpose of a conjugate. There's one dash. That's what the difference between I can see between the symmetric matrix and Hermitian matrix. That D.
I think there is some problem from that side. Wait a bit.
Hello, am I audible?
Okay.
Yeah.
Yes, sir. Now you're audible.
Yes.
Now you are.
Okay. So I lost the connection. So which basically means I lost my entire notes until now. Okay, but anyway, let's continue from we discussed this A star, right? A star equals to A bar transpose or E transpose conjugate, right? Correct?
Yes, sir.
So we talked about symmetric matrices to symmetric matrix to. For symmetric matrix in the real space. So symmetric matrix is defined for the real space. Okay. A equals to A transpose. Correct. A belongs to Rn. Okay. A belongs to Rn. So if A equals to A transpose, then it's called a symmetric matrix. Correct.
Yes, sir.
So for the hello, can you hear me?
Yes, sir.
Okay.
Sir, yes,
So
sir.
for the complex space. For the complex space analogous to the symmetric matrix is Hermitian matrix. Hermitian matrix. A should not be equal to A transpose. A should be equals to A star. Okay. A star is nothing but A conjugate transpose. Okay.
Yes,
If A equals to A conjugate transpose or A transpose conjugate, then A is said to be Hermitian matrix. Okay.
Okay, sir.
Sir, A conjugate is nothing but A star is nothing but conjugate matrix, right?
Yeah, A star is nothing but conjugate transpose.
Conjugate.
It's not just conjugate transpose. Okay.
So basically it means that for like if you have an n by m matrix, so the corresponding, for example, like for each element Aij should be the conjugate of Aki. Is
Exactly. Exactly. Yeah. You just got it directly. I'll explain that in a bit. Okay. So we'll take 5 minutes break and after that we'll continue. All right.
okay, sir.
Okay. Yeah. Thanks. Hello. Yeah. So let us continue. Okay. We have this until now we discussed about this Hermitian matrix, right? Okay.
Yes, sir.
Now, so as one of the student has pointed out, so when we mean this A star equals to A transpose conjugate, right? So generally, let's forget about this conjugate for a minute. For okay, when A should be equals to A transpose, what does that say? Aij should be equals to Aji, right? Am I correct?
Yes, sir. Yes, sir.
So when A should be equals to A transpose conjugate, what does that say? Aij should be equals to Aj conjugate, right?
Yes.
Correct. So,
Yes,
but
sir.
then, what about the case of I equals to j?
Yeah, that will remain this.
Aii should be equals to Aii conjugate, correct? So we have just talked about this. When for a complex number, when the complex number equals to its conjugate, what does that say?
It's a real number.
Yes. So when we have this Ai, right? I mean, what does Ai are the? It is a diagonal element, right?
Diagonal, leading diagonal.
Correct. Yeah. So basically, for a Hermitian matrix, diagonal elements are real. Diagonal elements are real numbers. Okay. So that is the, I mean, that is the first inference which we can take. Okay. So let us look at. We covered first lecture. Now we are moving on to this second lecture. Okay. In the first lecture, what we have covered is this, the inner product. Okay. The length of a vector, the basics of this complex numbers which we have covered, some of the properties, the conjugate transpose. Okay. And this is nothing but this AB whole star. This AB whole star is nothing but this B star A star. Okay.
Sir, sorry for interrupting.
Yes. Yeah.
But yeah, these PPT slides, I mean, these lecture slides are not available in my dashboard.
Right. Yeah. We will share it soon. Okay. We'll share it soon. Okay. So we looked at the definition of this Hermitian matrix. Okay. And then so is Hermitian matrix has some of the properties. One of the important properties is that if A is a Hermitian matrix, then all the eigenvalues of A are real. Okay. So let us look at the proof for it. This is an example. Okay. So here A was taken as 2, 5, 3 minus 3, and 3 plus A. You could observe that here all the diagonal elements are real. Okay. And then Aij is nothing but the conjugate of this Agi. Okay. So basically A is a Hermitian matrix. All right. So and then they have computed for this eigenvalues using this characteristic polynomial. They found that lambda 1 equals to 8 and lambda 2 equals to -1. Okay. 8 and -1 which are nothing but the real numbers. All right. So but the proof for it, the actual it was also mentioned here. Okay. We have this so we have this Ax star, right? We have this X equals lambda x, correct?
Yes.
We have this X equals lambda x, so Ax star is going to be equals to lambda x whole star, which is nothing but lambda bar conjugate. Lambda assuming it to be a complex number. Okay. We just generalize it. Okay. Assuming lambda to be a complex number, it should be lambda bar x star, correct? So similarly, if we take up this x star A star, A star ax whole star is nothing but this x star a star, which is nothing but this lambda bar x star. Okay, multiplying it by x, we get this lambda bar x star x. Okay, so we have this x star x equals to lambda bar x star x, and then this ax can be replaced by this lambda x, since we know this ax equals to lambda x. Okay, when lambda is eigenvalue. Okay, and x is the eigenvector. Okay, so yeah.
Okay, yeah, you were just doing that lambda equals lambda bar. Okay.
Yeah. Okay. So we have this ax are replaced by this lambda x. So x star lambda x is nothing but lambda bar x star x. So by just by rewriting this, we get this lambda x star x equals to lambda bar x star x. Okay. Lambda should be either x star x should be 0. When we have this x star x equals 0, which basically means the length of the vector x is 0. Okay. As I have already told, the length of the vector x is nothing but the squares of individual complex numbers lengths root, right? Correct. So when that is 0, what does that say? The length of each individual complex number is 0, which basically means it is a 0 vector.
So can you repeat that?
Okay, I'll repeat this. So I have told that length of a complex vector, I mean the square of length of complex vector is nothing but C1 C bar plus C2 bar plus C3 bar plus and so on, right? Correct?
Yes.
This is nothing but this R1 square. I mean, considering this R1 as this length of this complex vector plus R2 square plus R3 square plus and so on, correct? So when we have this, so suppose if this is equal 0, what does this say? R1 should be positive, R2 is positive, R3 is positive, and so on, everything is positive. Okay. When all of this is 0, which basically means R1 equals to R2 equals to R3 equals to and so on, Rn equals 0, correct?
Yes.
Am I correct? This one, no? You are not following me?
Yeah, the distances would be easier.
Yes. So the distance of, which basically means the length of each individual complex number also will be 0, which basically means it is just an origin, right? Which basically means C1 is 0, C2 is 0, C3 is 0, and so on, everything is 0. So which basically means C is a 0 vector.
Okay, yeah.
C is a 0 vector. Okay. Clear?
Yes, sir. Yes.
Okay. So basically, when we have this lambda into x star x equals lambda bar x star x, the only two possibilities are either x star x should be 0. Okay. For x star x should be 0. X is an eigenvector, so it cannot be 0. Okay. It cannot be a 0 vector. Okay. So that is why lambda should be equals to lambda bar. All right.
Okay.
When lambda, clear?
Yes, sir.
Yeah. So we have this lambda equals to lambda bar, which basically means lambda is a real number. Okay. We have already talked about this. When C equals C bar, C is a real number. So lambda is a real number here. Okay. That is the first property for Hermitian matrix. All right. Clear?
Yes.
Yes, sir.
Okay. So where we have used the property of this Hermitian matrix is here. We have replaced this A star by A. Okay. Since we have replaced this A star by A, we got this thing of lambda as real. Okay. Yeah. Moving forward, the other important property is that if A is a Hermitian matrix, then eigenvectors corresponding to different eigenvalues are orthogonal. Okay. So for this two we have a proof here. Okay. So we have this x equals lambda 1x, and then x is a vector X is the eigenvector corresponding to the eigenvalue lambda 1, and then Y is the eigenvector corresponding to the eigenvalue lambda 2. Okay. If lambda 1 is not equal to lambda 2, then what we should be proving is X dot Y is 0. Okay. The orthogonal means that they are perpendicular, right? Which basically means that this dot product should be 0. Okay. The dot product or inner product should be 0. Okay. Clear? Just like we have for the real case, we have this X dot Y should be 0. I mean, we should be proving that when lambda 1 is not equal to lambda 2, then X dot Y should be 0. Okay. So we took the example here. I mean, the same example which Sir has taken here. Okay. So he took it by an example. I mean, he calculated the eigenvalues, and corresponding to eigenvalues, he got this eigenvectors. Thereby, he proved this X dot Y is 0. But then we could take the generalized proof also. Okay. Instead of taking example, we could look at the generalized proof. So the way you do this. Let's say we have this X equals lambda 1x and then AY equals lambda 2y. Okay. So we do this X dot AY. Okay. X dot AY. AY can be replaced by lambda 2y. Okay. Which is nothing but lambda 2 into X dot y. Okay. And then similarly we have this. Yeah, X dot AY by the definition of this dot product, right? X dot AY equals to X star of AY. Okay, I have told you that X star is nothing but X conjugate transpose. Okay,
Yes.
X conjugate transpose. That is why we can write this X dot AY as X star AY. Okay.
Yes.
Okay. Since A equals to A star, we can replace this A by A star. Okay, and this X star A star can be replaced by AX whole star. Like there is this property of AB whole star equals to A star B. AB whole star equals to B star A star. Okay, like we have for this AB whole transpose equals to B transpose A transpose. The same property here. Okay, which basically means now we can replace this AX by lambda 1x. Okay, we have this AX equals lambda 1x. Okay, and then so AX whole star is nothing but lambda 1x whole star here. Okay, lambda 1x whole star is nothing but, you could write this as lambda 1 star into X star. Sorry, you could write it other way also. X1 star into lambda 1 star. Since lambda 1 is a complex number, not a vector, you could directly write it as lambda 1 bar. Okay, which will basically give. Okay, just are you able to follow from here to here?
Yes, sir.
Okay, so lambda 1 X whole star will give you X star into lambda 1 star. Okay, lambda 1 star is nothing but lambda 1 bar. Okay, because lambda 1 is a complex number, not a vector. Okay, and this you can take that lambda 1 bar outside, and which will give you lambda 1 bar X star Y. X star Y is nothing but X dot Y. So I could directly, I will be ultimately getting it as lambda 1 bar of X dot Y. Okay. So if you follow this equation 1 and equation 2, okay, X dot AY you got it as lambda 2 into X dot Y in the first equation. X dot AY in the second equation you got it as lambda 1 of X dot Y. Okay. Based on this, what we should be getting? Lambda 2 X dot Y equals to lambda 1 X dot Y. Okay, but then we know that lambda 1, lambda 2, they're already not equal. Okay, and then their eigenvalues, they cannot be 0. Okay, so that is why we get this X dot Y as 0. Clear?
Yes, sir.
Clear, right?
Yes, sir.
Okay.
So over here to in that step 2, you did that. You replace lambda 2 or lambda 1 bar with lambda because of the real valued nature. Right?
Can I repeat? Lambda 1 bar by?
In step 2, that in the last step, that lambda 1 bar times X, you replace that with lambda 1 just because it's real, right?
Yeah. We know that all the eigenvalues for a Hermitian matrix are real. from this first loop. Okay.
Yes.
Yes. So
what happened in this case,
uh,
since you have considered lambda 1 is not equal to lambda 2, that means the two eigenvalue is distinct.
correct.
But what happened in the same scenario, if lambda 1 equal to lambda 2, then can I conclude this is a dot product?
See, if you have this lambda 1 equals to lambda 2, which basically means you're talking about the same eigenvalue and same eigenvector. Right. That is kind of like no-brainer, right? I mean, see, we have this, let's say ax equals to lambda 1x, okay? You're talking about ay equals to lambda 1y. When you mean by lambda 1 equals to lambda 2, correct? When you mean by lambda 1 equals to lambda 2, you're talking about the same eigenvector and then in that case, x also will be equals to y.
Then no point to this.
Yeah. There's no point in looking at that scenario, I'm saying. Okay? Yeah. You got it, right?
Yeah. Okay.
Yeah. Okay. So this part, like.
So is this we had in the earlier case, right? Like symmetric matrices, like we can say that they are diagonalizable, right?
Right.
That means that it has n eigenvectors, right? So that means that each of those lambdas will be unique. So can we say something like that about this Hermitian cases?
No, that need not be the case actually. So let us look at symmetric matrices case, okay? So even for the symmetric matrices, you have this case of for the different eigenvalues. For the different eigenvalues, we have this corresponding eigenvectors are orthogonal, right? For symmetric matrices.
Yeah. Yes.
Correct. And then there you have the case of let's say the matrices are diagonalizable. Okay, all the symmetric matrices are diagonalizable. Correct.
Yes.
Right. So when all the symmetric matrices are diagonalizable, you're also considering the case of where you could have the case of same eigenvalue. I mean, let's say let's consider the case of this identity matrix 1001. 1001 is a symmetric matrix, correct?
Yes.
Correct. And then it has only one eigenvalue, lambda equals to 1. Correct?
Yes.
Yeah. So but it is still diagonalizable, right?
Yes.
Okay. So all irrespective of whether it has a distinct eigenvalues or not, all the symmetric matrices or all the Hermitian matrices can be diagonalized. Okay. Yeah. Okay. So we have this: if x and y are orthogonal, show that xy is a linearly independent set. Okay, this is kind of like no-brainer, right? When we have this x and y are orthogonal, then xy form this linearly independent set. Correct?
Yes.
Right. So this is just the same point which you have from the week four, I guess. Okay. Suppose we have this could be extended for n vectors also. Let's say you have 3 vectors of this xyz which are like mutually orthogonal. Okay. Then xyz form a linearly independent set. Okay.
Yes.
Clear? Okay. So that's what we have. This is just this diagonalizable part, okay, which will come later. Okay, the diagonalization of Hermitian matrices, that is just a crux of this week 5. Just like you have done for this diagonalization of symmetric matrices, we'll do that also. Okay. So until now we looked at the Hermitian matrices, the property of Hermitian matrices. Hermitian matrices is nothing but similar to this symmetric matrix, correct? Now we have this one other important matrix in the real case, which is orthogonal matrix, right? Correct. What is the orthogonal matrix?
Orthogonal means the dot product will be 0.
What? Orthogonal
Orthogonal
matrix. Yeah. What is orthogonal matrix?
Q transpose is identity matrix.
Yeah. Right. So we have this.
Okay. Okay, I thought vectors.
Can you repeat?
No, I was like, I thought orthogonal vectors.
Q transpose equals to I, or Q transpose Q equals to I. This is Q belongs to Rn, okay, real space. Then Q is called orthogonal matrix.
Yes, sir.
Okay. Can someone tell me some of the properties of orthogonal matrix? Okay, it's okay.
Yeah.
Dot products of columns are 0.
Can you repeat?
Dot products of the columns are 0.
Oh, the dot products of
it is
different
columns in the
columns are zero.
matrix.
Different
Matrix
columns.
is
Important thing is orthogonal matrix have eigenvalues of 1 and
Yeah, like the modulus of eigenvalues is 1, right?
yeah, I mean that, yeah.
Right, not the eigenvalue could be plus or minus 1.
Yeah, plus or minus 1.
Okay. Yeah. Now we look at this complex case, the complex vector space. Okay. Here, instead of this transpose, we have this A star equals to I. Okay. Or A star A equals to A star A equals to I. Okay. You know that A star is nothing but a conjugate transpose. Yeah. Or A transpose conjugate. Okay. And just reiterating this wherever possible so that it will become more and more clear for you. Okay. Yeah. So this is then here A is called as unitary matrix. Okay. Unitary matrix. All right. Clear? So this is just this analogous to this. This is just similar to orthogonal matrix.
So orthogonal is for real value.
Yeah. Orthogonal is for real values. This is for this complex. Okay. Abhi tak
Sir,
clear?
sir, A bar is also conjugate matrix only, right? Conjugate matrix of A, right? A bar means
A bar is conjugate matrix, but A star is conjugate transpose.
conjugate transpose we call this A.
Okay, conjugate matrix is we have conjugate matrix A, that is A bar. A bar is, A transpose is normally transpose. You combine both, then it will become A star. Okay.
So
So I mean,
Yeah.
Do the other properties follow as well? Like is it analogous to the orthogonal?
Diagonal as well?
No. In orthogonal, you have like the vectors are orthonormal and things like that. Like, can we say the same about this unitary as well?
Right. Yeah, you could say the same about this unitary as well. Okay, so we have this, and what do we have? We have this A star A equals to I, right? Correct?
Yes.
So let's say I have this A equals to this is C1, okay? C1, I'm just assuming this C1 is one vector, C2 is another vector, C3 is another vector, C4 and so on, Cn, okay? This is A, okay?
Yes.
What is A star?
Maybe C1 bar.
Yeah.
horizontal.
C1 bar, right? So this is nothing but this one.
Yes.
Can I write it this way?
Yes, sir.
Okay, and so on. C1 bar, correct?
Yes, sir.
So based on this, you'll get one important inference, I would say. Okay. A star A equals to I, okay, which basically means C1, C2, sorry, conjugate, okay, Cn conjugate. This is A star, okay, multiplied by A.
C1, C2,
C1,
Cn, C2,
C2, C3, and so on, Cn, correct?
Yes, sir.
So, I mean, forget about A star A equals to I. What will be the first value here?
1.
C1 conjugate, C1, right? This will be the first
Yes.
value.
Yes.
This multiplied by this is the first value, right?
Yes, sir.
Correct? So, and
Yes,
then
sir.
what's going to be the second value? It's going to be C1
C2
conjugate
by-
C2, C1 conjugate C3, and so on, C1 conjugate Cn, correct?
Yes, sir. Yes.
So, this is going to be C2 conjugate C1.
C2, C1.
Yeah.
C2, C2, C3,
Yeah, C2, C2,
C3,
and so on.
C2,
Okay?
C3, yeah.
Yeah, C2 conjugate C3, and so on here. So
Yeah.
similarly, you will fill all of this, and then you have here Cn conjugate C1, Cn conjugate C2, and so on. Cn conjugate Cn. Okay. I'm not able to write it here because I don't have any space there. Okay. So considering A star A equals to I, what does that say? This C1 conjugate C2, C1 C2, okay. C1 C1, C1 C2, C1 C3, and so on. C2 C1, C2 C2.
Diagonal elements should be equal to 1.
Correct.
Yes.
Correct. Yeah.
But is there any proof that I can do like C1 conjugate C2 is equals to 0 or?
Yeah. And I was coming to that part of it. Okay. I was doing all this to show that. Okay, and so on. We have this Cn C1, and so on. We have this. Okay. You have this equals to 1, 0, 0, 0, 0, and so on. 0, 1, 0, 0, 0. 0, 0, and so on 1. Okay. So what does this say? C1 conjugate C1 equals to 1, correct? C1 conjugate C2 equals 0. C1 conjugate.
Rest of everything is 0.
Yeah, rest of everything is 0, correct? Similarly, whenever I have this Ci conjugate Ci, then it's going to be equals to 1. Ci conjugate Cj is going to be equal to 0 when I not equals j. It's going to be dot product. Huh?
Yeah, this is dot product rule.
Okay. I mean, which basically means it's nothing but C1 dot Cj. Right?
Yes, sir.
Sorry, Ci dot Cj. Okay?
Ci dot Cj.
Ci dot Cj is 0, which basically means I and j are, I mean, columns I and columns j are orthogonal. Okay?
Is there any proof for this? Actually, that's what I'm asking. Is there any proof for this?
This is the proof, right?
No, I'm asking like Ci conjugate Cj when I is not equals to j equals to 0. So yeah, this part actually. How are we proving this?
Proof for this you are saying, huh?
Yeah.
See, we have this A star A equals to I for a unitary matrix, right?
Yeah.
When A star A equals to I, what is A star A? A star A is this value, this matrix, this big matrix, okay? Which is equals to I, okay?
Okay.
When we have it equals to I, what are all the zero values? Zero values is a CI conjugate CJ. Okay, CA conjugate CJ. For this case, I mean, when I naught equals CA, it is equal to 0. That is the identity matrix, right? See, this is of the form of Aij. Okay, Aij equals 0 when I naught equals j. Okay, Aij equals to 1 when I equals to j. Correct. This is for the identity matrix.
I think, sir, he is asking for, do we have any mathematical proof for C1 conjugate C2 is equal to 0? Is there any mathematical deduction where we can say this is equal to 0? So what we are saying, since this equal to 0 means C1 is orthogonal to C2, C1 conjugate. That is fine. That is comes under inner
this is not
product
proof,
dot
right? You are just taking the value from the matrix, unitary identity matrix, and putting it here, right? Ci conjugate Cj. But this cannot be the proof, right? I mean, from left hand side, you cannot go to right hand side.
He's asking for, is there any mathematical proof from the left hand side to reach to this 0 value?
Okay,
I think
from the
he's
left-hand
asking,
side,
yeah.
From the left hand side to reach to this.
Yes. I think he's asking for this.
No, like we should be going from the definition, right? From the definition, A star A equals to I. Okay, this is the definition. This is the definition of this definition of unitary matrix. Okay, I'm just using that definition to say that Ci like the vectors of the unitary matrix are orthogonal. Okay, I'm just using the definition.
This is same actually, sir. So in complex plane, anyway, if you do like I square equals to 1, and let's say I dot j, like I in the sense I and j are direction of x, y, z directions. That in case if dot product I dot j is always 0. In complex plane, if you do this is evident, but I'm asking for a proof actually.
He's asking whether the corollary will also be true.
No, it cannot be a corollary. There is a
no.
proof.
I mean, see.
Okay. You're talking about the corollary, like.
No. What I'm saying is, can I just say one thing? Like, see, if you consider the top row, wherein C1 conjugate C1, C1 conjugate C2, C1 conjugate C3. So starting from C1 conjugate C2 till C1 conjugate CK or CN, everything is 0 means all are similar. The C1 should be similar to C2, C1 is similar to C3, C1 is similar to C4. So all should be some similarity will be there, which makes them 0, something like nullify.
It's not similarity, it's orthogonality.
No, some nullification only makes it 0. Those what I'm saying. How can one complex conjugate like for instance, C1 conjugate can nullify with every other pair, like C1 conjugate C2 is 0, C1 conjugate C3 is 0, C1 conjugate Cn is 0. So I think C1 is similar to every other C2, C3, C4 in some manner, which makes it nullify, that their pairing nullifies, makes it 0.
I think proof is there in the SOM series, but I don't remember.
What's going to happen is, see, we have this in orthogonal vectors. Okay, C1 to Cn, they're all in orthogonal vectors. I mean, where each vector is orthogonal to each other. Okay, they form a basis of this n-dimensional basis. Okay, in cross n basis, they form that n-dimensional basis they form. Okay, it's like this. It's like that 1001 basis, right? 2-dimensional basis. They have this 10 vector and 0 vector. They form a basis, right? It's the same thing. Am I making sense?
Okay, so you can go ahead, sir. I too don't understand the question which I'm asking you, but I just seem to see some similarity which every C1, C2, C3, every other vector has with other. Otherwise, every other pairing will not become 0. Maybe one pairing will become 0, the other pairing will become non-zero. But if C1's combination with every other complex number like C2, C3 makes it 0 means, I think some similarity is there. which makes
actually the proof can be drawn up from how conjugate matrix happens, because if you see the I and J wise, so it's I and J, so index wise the sign changes of the complex parts, and I don't remember the proof now, but I think it's in the Schur series book actually, but I have studied for like long ago, so I don't.
But here Schur said ki this A star A is equal to identity matrix. So this is by definition. Now, if I compare these two, means one side, the left hand side, the identity matrix, and right hand side, this matrix C1, C2, C1, C1, and compare each term by term, then this will come C1 equal to 1, C1, C2 is equal to 0.
Yes, exactly.
Yeah, but this is the proof to that I don't know.
Okay, so
yes, sir. Let's move on.
Like let's just move on from here. Okay, so one thing you need to understand here is that, I mean, the key takeaway I want you to know is that all these matrices, all these vectors C1 to Cn, which form this unitary matrix, they're orthogonal to each other. Okay, the same is the same thing is true for this orthogonal matrix too. Okay, the same exact thing is true for the orthogonal matrix. Okay, and then the length of each vector is 1. The length of each vector is 1 because C1 dot C1, that should be equals to 1, right? That is why the length of each vector is 1. Okay, or you could say that they are unit vectors. Okay. Okay, moving forward. So we have this U star equals to I, or this orthogonal matrix, no? A inverse equals to A transpose. Here we have U inverse equals to U star. Okay. Okay. So this is just an example for the checking you use unitary or not. All you need to do is you just need to find U star and then multiply. You will get the unitary matrix. Okay. If it is a you'll get identity matrix. If it is a unitary matrix. One important thing is when you multiply this unitary matrix, that is you do the linear transformation of any vector with U. It does not change the length of the vector. Okay, Ux is the linear transformation of this vector x, right? So modulus of Ux is still going to be equals to modulus of x. Okay, the proof for that is given here. Okay. Ux dot Ux is nothing but the Ux dot Ux. It's going to be, okay, you could just take it this way. Ux dot Uy equals to Ux star Uy. Ux star can be written as x star U star. Okay, so which gives you U star U, which is nothing but I. Okay, U star U is I. So basically Ux dot Uy can be written as x star Y. Okay, or x star y. Similarly, when you take this x equals to y, which basically means ux dot ux equals to x dot x, which is nothing but this modulus of x whole square, the length of the vector. So basically, the linear transformation of x with respect to unitary matrix does not change the length of the vector. Okay, clear?
Yes, sir.
Okay, so the same thing can be used for getting these eigenvalues. Okay. So when we have this ux equals to lambda x, right? Okay. For the definition for eigenvalue is that you should be having ux equals to lambda x, correct? This is the definition for this for this eigenvalues, no? Where x is eigenvector, then lambda is the eigenvalue. Okay, we have already seen that modulus of ux does not change. Modulus of x is going to be equal to modulus of x, which basically means modulus of x is going to be equals to modulus of lambda into modulus of x. Am I correct? Which basically means modulus of lambda equals to 1. Okay, am I clear? This one, this part?
Yes.
Is this clear?
Yes.
Yes, sir.
Okay, so the eigenvalues, right? The length of the eigenvalue, it should be equals to 1 for a unitary matrix. Okay. Yeah.
Yes.
So the proof for that is mentioned here. The eigenvectors be different eigenvalues are orthogonal, just like Hermitian matrix, and just like the symmetric and the orthogonal matrix. The eigenvectors corresponding to different eigenvalues are orthogonal. The proof for that was mentioned here. Okay, ux equals lambda 1x and dy equals lambda 2y. You can take this x dot y as this ux can be rewritten as lambda 1x, lambda 2y, which is lambda 1 bar lambda 2 x dot y. Okay. X dot y equals to lambda 1 lambda 2 of x dot y, which basically means lambda 1 bar lambda 2 minus 1 equals to x dot y equals 0. Lambda 1 is not equals to lambda 2. So that's why lambda 1 bar lambda 2 is not equals to 1. Okay. I mean, this can be equals to 1 when lambda 1 equals to lambda 2, right? Otherwise, it won't be equals to 1. So that is why x dot y equals to 0, which basically means x and y are orthogonal vectors. Okay. Clear?
Yes.
Yeah. Okay. So after this, we have this thing of this diagonalization. Okay, where if A is a Hermitian matrix, then there exists a unitary matrix such that A equals to U. Okay, U this lambda vector, lambda matrix used, where this is a diagonal matrix. Okay, this is a diagonal matrix, just like the case of you have seen for this diagonalization of symmetric matrices. The same thing can be done for this complex vectors. Okay, complex space can be, same thing can be done. Okay. The way you do that is, I mean, the proof for that, it was mentioned. If you've gone through this notes, right? Here it was mentioned in an easier way. Yes, so we have this. You have this A into B1, B2, and so on, this B1, Bn equals to this lambda 1. So which basically you do the inverse of it. A will be equals to this one multiplied by this diagonal matrix with the inverse of it. Okay. AQ equals to QD, and then this is this Q matrix. Okay. This is the Q matrix, and this is the Q matrix again. AQ equals to QD, which basically gives A equals to QD Q inverse. Okay. But the thing is this for this for the case of symmetric matrices, this Q inverse is going to be equal to Q transpose. Okay, so that is how you get this. That is how you get the same case of A equals to U to U star. Okay, I mean U to U star. There you have in the real space, you have this A equals to U to U transpose. I mean where you consider this U as a orthogonal matrix, but then in the case of this complex space, we have this A equals to U to U star. Okay. I mean in this particular case, this T is upper triangular matrix, and this A need not be this A need not be Hermitian matrix. This A equals to U to U star, it will be applicable for any matrix, any n-cross-n matrix. Okay. This theorem is called this is called as a Schur theorem. Okay, we can use the Schur's theorem to prove that A equals to A equals to U lambda U star, where that lambda is this diagonal matrix. Okay, right now, if you do not consider this A as a Hermitian matrix, I mean, then this need not be this diagonal matrix. It could be upper triangular matrix. Okay.
If A is not a Hermitian.
What? Like in this particular case, this for this any matrix. I mean, when A is a Hermitian matrix, then this diagonal matrix. Okay. Clear?
Yes.
No?
Yes.
Okay. Okay. So we just prove this, and after that we'll come back here. Okay. This is called as the Schur's theorem. Okay. So any n-cross-n matrix is similar to upper triangular matrix T. There exists a unitary matrix such that A equals to UT U star. Okay. This is for any matrix, any n-cross-n matrix. All it requires is it is a square matrix. That's it. Okay. So we have this. We have here like Sir has taken an example for this n equals to 3. Okay. N equals to doing this. What we'll be doing is we'll take from the characteristic polynomial. We'll be finding one eigenvalue, and corresponding to that eigenvalue, we'll get an eigenvector. Right?
Yes,
we'll get the eigenvector Z1. Okay. We'll use Z1 and then find 3. Hello? Yes. Does someone have a doubt? Okay. So since this is a 3 matrix, okay, corresponding to this, as I already told, for you to get a unitary matrix, the column should be orthogonal. Okay, the column should be orthogonal. You get Z1 as one eigenvector. Okay, you get Z1 as one eigenvector. I mean, perpendicular to this, I mean, that is orthogonal to this eigenvector Z1. Other eigenvectors U and V. Okay, this U and V could be anything. All it requires is U and V should be orthogonal to this Z1, and U and V should be orthogonal to themselves also. Okay, that is you see here. Z1 star U equals to Z1 star V equals to U star V equals 0. Okay, this is not 0. This is 1 actually. I mean, the modulus of Z1, modulus of U, and modulus of V should be equals to 1. Okay, it's not 0. Okay, that is a typo there. Okay.
So from
Clear?
from this characteristic polynomial, when we find the first eigenvalue and the corresponding eigenvector after finding Z1, then we need to find all the bases to go ahead.
I mean, this is just like for the proof for the Schur's theorem. Yeah.
Then to find the basis, then what method we should apply to get the basis?
What you could do is you could solve it. This is 3 cross 3, right? This is 3 cross 3, correct? So what should be happening is
n equal to 3 means 3 cross 3. Yeah.
So you should be doing this. You have Z1, okay, and then you could assume it this way. Okay. That let's say you have this Z1, okay, Z1 star U. I mean Z1 dot product U is 0, right? So you could assume this U to be 1 x y, okay, 1 x y, okay. And then you could solve for this. Okay, from this you'll be getting one equation. Okay, and then we have this V you know Z1. Okay, and then you're assuming this as U as this 1 x y. Okay. Again we need to be wishing for this P, right? So when you have this as like 1 x y for V, since you need this U dot be as 0. You need to be getting it as and then Z1 dot V also should be equal to 0. So we have total of using this we'll be getting one equation. Z1 star V equals 0. Using that we'll be getting one equation. The other one is that this if you exceed x1 y1, this one has x2 y2, u dot v should be equal to 0. Okay, I think what you could be doing is you could take this as 1. Okay, since you need like any vector, I mean if you take kind of like 3-dimensional vectors, right? If you take one vector and the two vectors which are like perpendicular to that, it's going to be entire plane. It's going to be entire plane. You'll be getting like so many different possible vectors. Okay, it's not just one vector. So what you could be doing is you could take this u as 1 x1 y1 and then v as 1 1 y2. Okay, and then you could do this z1 dot u as 0 and then u dot v as 0 and then z1 dot v as 0, z1 dot v as 0. Using this you'll be able to first using z1 dot v, since only here y2 is unknown, you'll be getting the value of y2. Okay, once you get y2 using z1 dot u is equal to 0 and u dot v equals 0, you can get this x1 y1. Okay, is it clear what I have told?
Okay. No, I'm not getting why you are considering that as a 1. Why not 0?
This one, yeah, you could even take it as 0 also. Okay, it doesn't matter. Okay, like the thing is there are going to be entire set of vectors. Okay, that is why you could just assume like 2 values and then the corresponding y2 value will be changing. Okay.
Just somewhat like the middle space thing.
Yeah, more exact calculation of this, how to get u and v from the z1. Okay, I will look at it and then like I will let you know.
Okay.
Okay, so let's say like you have this z1 u v. Okay, you'll be getting this orthonormal basis where z1 u v they're like orthogonal to each other, and then the length of each of them is 1. Okay, now if you do this AU1, okay, AU1, here U1 is this Z1 ZUV, right? So it will basically give you lambda 1 Z1 AU AV, right? Okay, and this lambda 1 Z1 we got because AZ1 equals to lambda 1 Z1. Okay, so now if you do this U star AU, okay, U star AU, U star is nothing but this conjugate transpose. So that's why they have done this conjugate for the Z1 and then transpose. Okay, so you'll be getting this as Z1 transpose lambda 1 Z1, that will be the first value. Z1 transpose lambda 1 Z1, that's going to be the first value. Since Z1 transpose Z1 equals to 1, because modulus of Z1 equals to 1, you'll get the first value of lambda 1. Okay, you'll get the first value as lambda 1, and then this particular value, that is this first column value, this is going to be equals to u1 u transpose lambda 1 z1, correct? U transpose lambda 1 z1 is going to be this particular value. Since u transpose z1 equals to 0, because u1 z1 are perpendicular or orthogonal to each other, u transpose z1 is going to be equal to 0. Similarly, v transpose z1 is also going to be equal to 0. Okay, but we cannot be saying that about this value. U transpose AU, that need not be 0. Similarly, U transpose AB, that need not be 0. Okay. Clear? Why we got this value as 0?
Yes.
Is it clear? Okay, I hope it's clear. Then moving forward, so similarly we could do this for 2 cross 2 matrix also. Okay, for this 2 cross 2 matrix also, we could be finding one diagonal value. I mean, we could find the eigenvalue for this 2 cross 2 matrix. We could find the eigenvalue, and then we could do the same thing that is this. Hello, can you hear me? Hello, am I audible? Am I audible?
Yes, you're audible.
Okay. Yeah. So similarly, we have done this for here, right? So we made these two values as 0. Similarly, we could find one eigenvalue for this B matrix, that is this 2 cross 2 matrix. Okay. So we can repeat the procedure with B to get the eigenvalue lambda 2 of B. Okay. Such that P star P equals to lambda 2 star 0 lambda 3. Okay. Here also we did not get. We were not able to get exact diagonal matrix. We got only upper triangular matrix because B is not symmetric. Okay, B need not be symmetric. Not B is not symmetric. B need not be symmetric. Okay, that is why we'll be getting some upper triangular matrix. Okay. Now, if we got this P matrix, right? P unitary matrix. We can use the P matrix to get U2. U2 as 1 0 0. And then we can keep the P here, okay, which will basically give you, now U2 star U1 star AU1. Okay, this can be written as this way. Okay, 1 0 0 U2 star is this 1 0 0 P star. Okay, and then this U1 star AU1, which we got as lambda 1 star 0, and then this B matrix, right? Okay. Now multiplying this, what you get is this one we have already seen. This is lambda 1, and this is going to be some. Okay. One another, what to say, triangular matrix. Okay. So we get here also a triangular matrix, which basically means that this entire matrix is triangular. Okay, upper triangular. Clear? The way we have seen is, I mean, it could be all you need to look at is if you are able to follow it until here. The same thing we are like keep on doing it. Okay. To get the upper triangular in the next steps. Okay. That is, you are able to do it here. This also we need to upper triangularize. That is why we have done this. Okay. That is why we have done this. So what we could see here is, if you take this U2, U1, U2 as sorry, if you take U1, U2 as one matrix, that is, finally we got this U2 star, U1 star, A, U1, U2 as T, right? This U2 star, U1 star, A, U1 as T, upper triangular matrix, this one. So this U can be taken as U1, U2. Okay. U can be taken as U1, U2. U1 is a unitary matrix, U2 is a unitary matrix, so U1, U2 will also be a unitary matrix. Okay. So now what we have seen is, irrespective of what the matrix A is, we were able to get this as U star AU as T. Okay, U star AU as T, which will basically give you A equals to UT U star. Okay. Clear? By multiplying with U here, U on the left hand side and right hand side, we'll get it as U star AU. U star is, which will give you AU equals to UT, and again if you do that, it's going to give you A equals to UT U star. Okay. Is this clear? Do you want me to explain it at any part? I'll try to explain it again. Okay. So this is for the case of any matrix, right? Here we did not assume this A is a Hermitian matrix. That is, we did not assume that A equals to A star. We assume that A can be any matrix. Okay. But then if you have followed until this, we could use this for the next step, that is the Hermitian matrix. We have done that A equals to U star A, right? U star A or equals to U to U star, sorry. A equals to U to U star, okay? Now for suppose, let's say A is a Hermitian matrix, okay? A is a Hermitian matrix, which will basically give you A star equals to T star whole star, okay? Which basically means you could take this way UT as one and then U as other one. You could take this UT as A and then this as B, which will give you B star A star, right? Which is nothing but U star whole star of UT whole star. Okay. U star whole star is nothing but A multiplied by UT whole star is T star again. Okay. So A star equals to A, right? A star equals to A because A is a Hermitian matrix. So you replacing, yeah. So A star equals to A, which will basically give you A equals to U T star U star. Okay. So if you follow this, this is the first one. This is second one. From 1 and 2, what we could see.
Can you explain the second line again?
This one.
Yeah. That one. That line. Yeah. From here to the next line.
Okay. So UT U star whole star, right? A star equals UT U star whole star, correct? So you could assume this as A, okay? UT as A and this as B, okay? So what is this give you? B star A star, right? I mean, if you assume this as AB whole star, it is nothing but B star A star, correct? So replace B by U star here. Replace B by U star and replace A by UT. Okay. Which will give you this. U star whole star is nothing but U again. And UT whole star, you could just apply this AB whole star formula again, which will give you T star U star. Okay.
Yes.
Clear?
Yes, sir.
Okay. So which will give you again this U T star U star. Okay. I mean A equals to UT U star and A equals to U T star U star, which will basically give you T equals to T star, right?
Yes,
correct?
Yes, sir.
Okay, T equals to T star, which is nothing but T conjugate transpose. Okay. Correct?
Yes, sir.
That is the definition of the star, right? So generally T is of this form. T is, since it is upper triangular matrix, it is of this form. You have some zeros here. Okay. So basically it's going to be something like this, correct? Okay. This is also going to be 0. Okay, this is going to be something like this, correct? Now what's going to be T star? It's going to be the opposite of it, right? Now the zeros are going to be at the top. I mean, of course, you could do this conjugate, I mean, not there, but here. Okay. Okay, this is going to be T star, right?
Yes, sir.
Correct. So this both are equal. These both are equal, right? What does that say? What
The
does
upper
that say?
triangle is also 0.
Yeah. So basically all these values are 0. Okay.
Yes.
And then even only the diagonal places are going to be there, and even there x is going to be equal to x conjugate. Even
Yes,
there x is
it's
going to be
real.
equal to x conjugate, which basically means it is a real
Real.
value. Okay. So which gives us this. Okay. I mean, we have proved that if like it is just a case of like when A is Hermitian, then instead of upper triangle matrix, you get a diagonal matrix. Okay.
Yes, sir.
Clear?
Yes, sir.
Okay. So we have seen the like the way to do this diagonalization is, I mean, for the summation matrix, the unitary matrix, it's going to be the eigenvectors itself. Eigenvectors itself. Let me show an example for this. Okay, this is just the proof for it. Okay, it was not mentioned there, but then the way you get this unitary matrix is the diagonalization is, let's say you were given a Hermitian matrix A. Okay, you were given a Hermitian matrix A equals to U. This U is going to be the eigenvectors of A. Okay, eigenvectors of A, the unit eigenvectors. That is, the length of those eigenvectors should be equals to 1. Okay, just like we have for this. And so on. Okay, just like we had for this diagonalization of symmetric matrix, right? The same thing occurs here. Okay, you have here lambda 1 and then lambda 2 and so on. You have here lambda n. Okay, and then this is going to be the symbol. Clear? So the way you do the diagonalization for a Hermitian matrix is, you just find an eigenvalue and then the corresponding eigenvector. If you write it in this form, that is the diagonalization of Hermitian matrix. Okay.
Yes, sir.
Okay. Yeah. I mean, that is just a entire summary of week 5. Okay. I understand that the upper triangulation, that's not entirely clear. Okay. And then the way you find the U1, I'll find out in detail about it. Okay. And then I just give you the clear cut straightforward way of like computing it. Okay. And then I'll try to mention that in discourse. Okay. But then once you get that idea, from there the way you move forward to this application for summation matrix, that is getting to know that the in the special case of Hermitian matrices, the T is not an upper triangle, it's directly a diagonal matrix itself. That's kind of like straightforward. Okay. And then yeah, if you know the eigenvectors and the eigenvalues, you could do the diagonalization of Hermitian matrix just like the way you did for the symmetric matrix. Okay. Okay, clear?
Yes, sir.
Okay. So yeah, that's it. And like, try to look at the problems. Okay. Try to look at the problems, and then if you have any doubts, you can just post it in discourse, and then we have a solve with us tomorrow. Okay. There we'll be discussing some of the problems. Okay. Clear?
Yes, sir.
Okay. Okay. So I hope this was helpful. Okay. And
Yes.
yeah.
Thank you so much.
Thanks.
Yes.
Thanks, everyone.
Thank you, sir.
Thank you, sir.
Thanks.
Thank you, sir.